OK, so the next thing I want to talk about before we start doing explicit examples and going through processes is how loops work in this effective theory. And we're going to have to come back and talk about our grid that we had for this split up of momenta and how should we actually think about it in practice. And then we'll also deal with how matching and running work. So I'm going to do this in the context of an example. And again, I'm just going to pick the simplest example that has only one jet, just to make our lives a little bit simpler. So we'll consider our heavy to light current. And I think actually once you see how it works in this example, you'll understand what all the general features are of doing loops in SCET. So we had operators that we constructed, lowest order operator. And let me write it in this way, which was prior to making our field redefinition. I can just write it this way if I want. And gamma, for B to S gamma, is a tensor operator. And there's the photon field, which is a field strength F mu nu. So let's just think of that as all part of the gamma. OK, and then that's also appearing here. And I could use the spin structure properties of these things to reduce the sigma mu nu, but that's not really going to be part of our story, so let's not bother with that. So what do? I just compute the QCD loops and the SCET loops, and I compare them. And if SCET is the right effective theory for this limit where I have an energetic photon and a back-to-back with an energetic strange quark, then I should match all the infrared divergences in that QCD computation. I should be able to extract a matching coefficient. I should be able to determine what the C is from that calculation. And I should be able to run the operator. I should be able to make this into MS bar, do some renormalization of this operator, and then do some renormalization group evolution of that Wilson coefficient. Well, let's just think about computing the graphs. So we have to decide when we compute the graphs how to regulate them, right? And we need to use the same infrared regulator in the full theory and the effective theory. So here's how I'm going to regulate them. We could do this different ways, and it's useful to understand that various answers that we get are independent of the regulator. So I'm going to take p squared not equal to 0 for the strange quark. So there's infrared divergences associated with the strange quark, and I'm going to take p squared not equal to 0 for them. I'm going to use dim reg for the heavy quark. So I could take the B quark to also be off shell. That would make the formulas even more complicated. So instead of doing that, I'm just going to allow epsilon to regulate the B quark. And these guys are pretty easy to track, so that won't be a problem. And I'm going to use Feynman gauge. I don't have to do that, but that's a nice gauge for doing calculations. So what are the diagrams? Well, I have my photon, and I have a vertex diagram like this. And then I have wave function renormalization. And so let me, in the usual kind of cavalier way, denote the wave function renormalization, which is just the multiplication by the appropriate z factors by diagrams like that. And this is a standard QCD calculation, and we can carry it out. And what does the answer look like? So this diagram here has double logs and single logs that involve p squared, which is our IR regulator. And then it has some terms that are finite, which I'll just denote by. So p here is the momentum of our strange quark going out, and pb is the momentum of our b quark coming in. And let me not try to, we're not going to talk much about these finite terms, but there is some. So terms with, what I mean by finite here is terms with no IR divergences. So the IR divergences are these single logs and double logs, and then there's some remainder that I can write that way. I'm expanding for small p squared. So p squared is not equal to 0, but I take the limit p squared goes to 0. And in that limit, these are the IR singularities. And then there's some function of b dot b, which is just an order 1 thing. And then b squared, of course, is pb squared. So that's sort of the remaining kinematic variables this could possibly depend on. No. It's really finite. There's no, so, yeah. Yeah, so let's see, I guess I carried out so there is a z for the tensor. And when I write this, yeah, let's see. So, OK. Let me do this. I think it's better. So I added up all these graphs, and I want to add one more. So there's a counter term for the tensor field. So let me change what I was going to say and do it this way. So the sum of these 4 graphs is this. Okay, so then there's no UV divergences. And I'll just tell you what the z factors for these 3 are, and then you could figure out what this graph is by subtracting the 2. So the tensor current in QCD has a z factor. It looks like that. There's a z for the heavy quark. And if I include the finite residue as well as the divergent pieces, this looks like this. I think I'm going to have to make one adjustment to my formula here. Let's fix something here. Yeah. So if I want it to be the way I say, then what do I have to do? So this guy should be 3/2. And there will be one more divergence. I think that's right. So this 2/epsilon IR here is that 1/epsilon IR. And the UV renormalization is taken care of once I have the Z tensor. That there's divergences in this diagram and these ones, but there's one left over, and that's taken care of by Z tensor. So there's no 1/epsilon UVs after I take care of this guy. Okay, so that's just kind of by the definition of what Z tensor should be. And then everything else is as I wrote. So there's IR divergences that are associated to the strange quark off-shellness. That's these two terms. There's an IR divergence associated to the heavy quark going on shell. That's that term. That's the sum of diagrams. OK, so what about SCT? So there's going to be in SCET collinear diagrams and ultrasoft diagrams. So I'm going to use Feynman gauge for everything again. This is not something I have to do. This is what I'm going to do. And let's start with the ultrasoft loops. So there's a vertex graph. So using the notation that we've adopted, where the collinear quarks are dashed and the heavy quarks are double lines, we have a diagram that looks like that. There's some prefactor. Let's focus on what the loop integral looks like. So this loop here, the k that's going through this loop, is just a residual k. There's no label k for this loop because it's an ultrasoft gluon. So when we write down all the terms in this loop, it's just standard field theory. There's nothing special about it. Since I'm taking the strange quark off shell, the propagator that I get is this shifted iconal propagator, where basically the fact that it's off shell gives me this extra term there. That's regulating some IR divergences. And we want that because we want to regulate the IR divergences in the same way in the full theory and the effective theory. This is proportional to that. And if I put in all the factors, so it does have double logs of the p squared. It doesn't have single logs of the p squared. And actually, if we look at the double logs, the coefficients also don't match with what we had over there. And so there's going to be some other diagrams that are going to involve double logs of p squared as well. One thing that we can note here is that if you think about the scales in the problem, remember that our loop integral was totally homogeneous in the power counting. The lambdas were totally homogeneous. And if you think about p squared as scaling like lambda squared, which is natural size for an external collinear momentum, right? If p squared scales like lambda squared, then so does p squared over m bar dot p. And this is a dimension 1 thing, and this is the ultrasoft scale, right? For some ultrasoft momentum. And so if you want to look at these logarithms and you ask what scale is this effective field theory diagram sensitive to, it's sensitive to the ultrasoft scale. So the logs are not large logs, they're order 1 logs, as long as mu squared, mu is of order lambda squared, which is the scale for ultrasoft momentum. And that's what we expect from this ultrasoft diagram, that it's telling us about physics at the ultrasoft scale, and that's what we see from setting things up, doing the calculation. So you could also think about a wave function diagram with an ultrasoft gluon. But this guy's 0, since in Feynman gauge, you just get n mu, which is 0. So there's no, so z for the collinear quark field from an ultrasoft loop is 0. That wouldn't necessarily be true in some other gauge, but in some other gauge, this diagram would also change. All the diagrams would change. And so if there was a non-zero contribution in this diagram, it would just be taking care of gauge invariance. And then finally, there's ultrasoft loop on the heavy quark. And that actually just gives us, that's an HQT diagram. Has nothing to do with the linear quark. And so from that diagram, we would just get the z factor, which is the appropriate z factor in HQET with R regulator. If I specify ultraviolet and infrared divergences, that's this. And this infrared divergence here is actually exactly the same as the one that we had over here. OK, so the ultrasoft sector is really just, there's nothing really tricky about it. It's just write down the diagrams, do the loops.
Sorry, for the electricity case, isn't that like IR divergences of those diagrams cancel with a real emission, with the evidence for the emission of a real P1?
It depends. So what are we looking at, right? So it depends on what we're looking at here. And what I'm doing, so yes, in general, that would be true, right? If you were calculating some cross-section, which was IR finite cross-section, and that, of course, would depend on defining what you mean by measuring this quark, right? So the IR divergence would become some physical scale, like the mass of the jet, or the IR divergences would turn into something physical, right? If you put this into a physical cross-section. And that's exactly basically what would happen. These p squareds would become sort of the mx squareds that we talked about when we talked about beta s gamma. But here what we're interested in doing is a matching calculation. So we fix the external states to have a particular number of partons, and we want to compare the full theory calculation with the effective theory. The effective theory should reproduce the infrared divergences. So really all we care about is not that this is infrared finite, but rather that it's got the right that the effective theory has the same infrared divergences. And we'll see that in the end, what you can think about is rather than canceling infrared divergences as you're thinking in the full theory, we match the full theory onto the effective theory. And that matching gives us the Wilson coefficient. And then we take the effective theory, and all the cancellations that you're thinking about between real and virtual graphs will occur in the effective theory too. So you can just think about the effective theory virtual and real graphs, and then the cancellation will take place there. But then you're thinking about that cancellation later at a lower scale, which is what you actually want to do, because what I just was telling you about IR divergences becoming different things in the final state becomes very trivial once you're in the effective theory. And we'll see sort of exactly how that works later on. But first, we have to talk about linear graphs. So in the linear graphs, we had graphs like this one, where we could take a gluon out of the vertex here. That corresponds to taking it out of the Wilson line. So let's label the graph in the following way. This will be k plus p, this will be p, this will be k. And if we follow our rules for what this is, we would write a sum over labels and then an integral over residuals. And let me put the residual integral in dimensional regularization. Let me try to squeeze in everything. Which won't be possible, but. So I'm going to write out the components to make clear who's the residual and who's label. So in the denominator, there's one more term. So the plus guys are always residual, and the perp and the minuses are always label. That's the short way of saying what I'm trying to squeeze in here. Okay, so the denominator has these three terms, this guy here, this guy here, and this guy here. Oops. And when I label the diagram like this, you should think that each of these has a label and residual part. So K, you can think of as a pair, K label, K residual for now. And remember the importance of doing this. The importance of doing this was related to always being able to identify what the lowest order term was on the right here. Okay, and that actually becomes more important once you start to think about diagrams where you would add like an extra ultrasoft gluon somewhere in this picture. Then of course when that ultrasoft gluon feeds its way through this loop, you've got to make sure that it's only the lowest order piece that's showing up. In this case here, it's really just, we just have a collinear loop. And we don't have any sort of real ultrasoft momenta from ultrasoft particles besides the heavy quark, okay? Which is just an external particle to the loop. So what we want to do with this is we want to turn it back into an integral. This way. And if it wasn't for these restrictions here, then that's very easy, actually. So I claim, and then I'll talk about why it's true, I claim that if we ignored the restrictions, and those restrictions are ensuring that we don't double count between our collinear and our ultrasoft degrees of freedom, so they are important, but let's ignore them for a minute. If we do ignore them, we would just get the following. Where I just basically stop thinking about residuals and labels, write everything as a full momentum, and write down exactly the same thing I just wrote. So this is a full k squared. And this is a full k plus p squared. Okay? So what I'm going to do is I'm going to first ignore these restrictions. And then I'm going to tell you how it would work, how like this actually does turn into this. What are the rules for doing that? And then I'll come back and I'll tell you what these extra conditions do. So really, in order to see, so this looks like maybe it's trivial, but we should think about it. And it's almost trivial, but not quite. So really what we're doing here is we're combining back together labels and residual momentum, right? And the place that we have to worry about that is in the perp in the minus space. And recall we had the grid. And the grid is sort of our way of our guidance to sort of see how to put things back together. So we had vectors that lived in this space, and this is the label, and then there's the residual if we want to point to some place in that space. This picture was like a Wilsonian effective field theory, because the picture makes you think of sharp edges. But the real effective theory that we're doing is a continuum one. And so you have to expand your brain a little bit and think that each of the boxes in this picture is actually an infinite space as well, because the residual space doesn't have restrictions like that that would spoil Lorentz symmetry. So each grid point really is specifying an infinite space of residual momenta. And it's R4, or it's Minkowski space. So the momenta components are real numbers. And there's some rules. So what are the rules? So I'll tell you what the rules are without restrictions for now. And then we'll come back and I'll tell you what the rules are with restrictions. So rule number one is the simplest, and it just says that say I had the following, and I'll use kind of a one-dimensional notation. Say I had a sum over KLs and an integral over all KRs. Well, that's just the same as not having split it up and doing an integral over everything. Because we split this thing into boxes, and if we really integrate over all boxes and sum over all labels, then we should just get back the full integration over all the momenta. So that's true for each, for minus and perp momenta. But really what we have to do is we have to do this with some integrand, right? So the type of integrand that we have is the following. If you think about the components, that we're talking about here, which are the minus and perp ones, then there's, in our integrand up there, there's no minus or perp residuals. So it's just a function of the labels. Right? And so what that says effectively is that this is a constant function in this box, in each of the boxes. And effectively, the way that you use this formula is you do the following. You say, well, if it's a constant function in the box, I could evaluate it at a different point in the box, and I'd still get the same value. So in particular, I could evaluate it at k label plus k residual. And then I can use that formula up there to say that this is just an integral with a continuous k of the function evaluated at that continuous k. So that's the way that sort of number one works. We are integrating functions that are constant in the boxes, and so then it's kind of trivial that we just how to put the boxes back together. Yeah.
So this dkr integration doesn't have kr plus.
Yeah. So what I mean by it is,
okay.
Yeah. So I'm using here for each minus or perp momenta a one-dimensional notation. Yeah. And so I have three of these. I have to do this, and for each one of them, it's true that what I'm saying. But of course, if I tried to write that on the board, then it would confuse the point, I think, which is in some sense a simple point. OK, so this is in some sense saying that this whole split up that we were doing was not really needed. We could have just written a continuous integral, and that's kind of what this is saying, right? That we could have just written a continuous integral and not worried so much about all this split up that we were doing. The place that we have to be careful about is these restrictions, and we'll come back to that. And the other place they have to be careful about is when you have the multipole expansion. But as long as you sort of take care of that, then basically this is always happening. So the reason why this works is the following. For every label loop momentum that there is in any diagram, there's always going to be some corresponding residual that's not specified by delta functions in terms of external momenta. And effectively, therefore, we can absorb in order to do what we just said. So we can always go back from this discrete type notation back to a continuous notation. The discrete notation was just helping us to set up the expansion and be careful about it. But we can always go back to the continuous one because there's always a KR that has this property that it's. Okay. So now, in general, though, you might have some more complicated thing. And if I'm going to give you some rules, I should sort of give you a complete set. So we have to append our list of rules by the following one. So if I thought about doing what I just said over here, but I went to some higher order, then what could happen? Well, then these kr minus and kr perps could show up. They'd never show up in the denominator of our propagators if they were just collinear propagators, but they could show up at some point in the numerator. And we need actually a rule like this one, which would be clear if we were regulating dkr in dimensional regularization, that the power divergences are getting set to 0. And that is basically to maintain the Lorentz symmetry in the residual space. We need a rule like this for j greater than 0. So that only doesn't come into our calculation, but include it for completeness. So when would these integral over kr actually do something non-trivial? It would do something non-trivial if we had ultrasoft loops and collinear loops at the same time. So in the case where we just have collinear loops, it's basically up to this issue about the restrictions that we'll talk about. It's basically that we just could have done everything as continuous and ignored this split. But if we have both ultrasoft particles that are sort of participating through the loops, so or and or, then these will give non-trivial, in general, these will give non-trivial loop momenta in the residual momenta. And hence, there will be some that we can't just absorb in the fashion that we just said. So there will be, in this situation, residual momenta. Some residual momenta will be absorbed in the same way to turn the integrals into continuous ones, but other ones won't be absorbed. And that's because the ultrasoft propagators, right, would involve LR, the LR plus, the LR minus, and the LR perp in the denominator. So we don't have this rule to apply. We can't do what we said here with the constant boxes because now the functions are depending on that variable. So we just have to do the integral. So you could have something that looks like, just in kind of a schematic formula, let's have there be two kr and an LR. We're in kind of an obvious notation. I'm saying that the function could depend on LR residual. It doesn't depend on KR residual. So we absorb KR back into the sum to make it continuous. And then this integral we just have to do. OK, but it's still, we're still, in the end, just doing an integral. This guy could come from ultrasoft propagators, for example. Okay, so those are the kind of different cases that you can get. But nevertheless, even if you have ultrasoft particles and propagators floating around, there will always be a residual momentum associated to the sort of what we were doing over here that you can absorb in the same way I stated. So let's proceed along these lines and see where it takes us, and then we'll come back and put in this additional restrictions.
So will you ever have to do a discrete sum? Like, is there a sum over LL?
Yeah, so you never have to do a discrete sum. Yep. The discrete sum is really just a way of thinking, and I'll show you in a minute that you even can avoid thinking about it once you know what to do. So it's guiding you towards the right answer, but it's not really something that you have to think about this grid picture. It's really just, if you get confused, you can always think about it, but if you're not confused, you don't have to think about it. Okay, so this guy is what we said, proportional to what we said. It's just to in this case, the reason why it was so simple is because there was only K residual is one component of this guy, and then there's these other three, right? And for the other three, we just absorb the sum and the integral back together, and there's nothing further to talk about. So that's why this is, in some sense, very simple. So we just do that. And what do we get? Get some 1 over epsilons. We get some logs of p squared. And I'm putting in even the constant term, since it's pretty simple, 4 minus pi squared over 6. So this is, we had a, if you think about where this came from, there was the place that this Wilson line came from was attaching this guy over here and then integrating out that off-shell propagator. So this is a vertex diagram. We had a vertex diagram which was an ultrasoft gluon, and now we've added an identical topology, except we drew it different because this line was off-shell. So we drew it as a Wilson line, and that's the right way of thinking about it. But if you think about where it came from, it was the same topology, and we've added another vertex diagram. So the effective theory has 2 type of vertex diagrams, this collinear one and the ultrasoft one, and we're going to add them together. And in this one, you see the logs are minimized at a different scale, mu squared of order p squared, which is the right scale for a collinear loop. Because remember, the collinear particles lived at a larger p squared than the ultrasoft ones. So this is there's a larger scale that would minimize these loops. It's the collinear scale. So the effective theory is capturing the physics at that scale. Squeeze in another diagram here. If we do the collinear wave function normalization, then this is non-zero. This was 0 for the ultrasoft gluon, but for the collinear gluon, it's non-zero. And it's exactly actually the same as the full theory. It's same as massless QCD. So you can do the diagram using the effective theory find rules, and that's what you find. But you could also understand why that's true. And the reason why it's true is nothing in this diagram really specifies a frame. We called all the particles collinear, but it's not attached to anything. So we could just take the whole diagram and kind of boost back to the frame where everything's kind of soft, and then we would be thinking about it in terms of the full theory field. So there's, yeah, and that's effectively why this diagram, like this, that doesn't have any kind of reference, unlike this one, which has a reference because it's attached to the heavy quark. That's why it's the same as QCD.
When you configured this loop, you needed the iepsilon prescription?
Yep.
How do you know what the iepsilon prescription for the Wilson line is?
Oh, for this one. Yeah, for this one, for this guy, it actually doesn't depend on the iepsilon prescription up to yeah, if I remember correctly. Yeah, that's true, I believe, when I'm being a little bit cavalier with it, but once I put in the zero bin restrictions, I'm not sure if that's true anymore. Like, yeah, I mean, really what solves that is that in a minute I'm going to be talking about the fact that there's a subtraction term here, and once you put the subtraction term in, that I0 is not relevant. But I think even if you do this diagram with arbitrary I0, because what's happening is that pole is m bar dot k going to 0 is related to some of these 1 over epsilons. And we'll talk about that more in a minute. Yeah, I'm not 100% sure. It could be that there's some sign that might flip. I'm not 100% sure. That then,
Even if you get the wrong side,
yeah.
the difference will be subtracted.
I guess I know that if, yeah, what I know is that, yeah, let me answer your question later. It'll be easier because I'm trying to say a bunch of things that depend on something else that I haven't explained yet. So, so what are the other possible topologies we could write down? So we could write down this one, where we take two attachments in the Wilson line and just loop them back up. But that's proportional n bar squared, and so that's 0 in our Feynman gauge. And likewise, there's kind of a looping back up in the vertex, in the wave function normalization, but this guy's scaleless, power law divergent. And so we can just set it to 0 in dim reg. You don't have to worry about it. OK, so that's all the diagrams. Let's think about doing matching, i.e., let's think about comparing QCD and SCT by adding up the diagrams. In QCD, we carried out the renormalization. We added the Z for the tensor current. Let me just write again what the answer kind of looked like. In SCT, we didn't carry out renormalization yet. So let me call this the bare SCT result for now. Once we add the ultrasoft and collinear diagrams together, the logs of p squared match up exactly with the full theory. So this is the first sign that we're really that it makes sense to be thinking about adding these loops, even though they were the same topology. We are correctly reproducing those logs of p squared in the full theory. And then there's some other pieces. I'll write out all the other pieces so you see what they look like. Well, maybe I won't. I won't write the constant. So there's all the effective field theory terms. So these terms here, we can match up with these terms here. So that's good. These terms here, which remember in the full theory were finite, and these terms here, which in the effective theory are finite, the difference of those is going to give the Wilson coefficient. Now, we said that the Wilson coefficient could be a function of p bar. So what's going on with that? Well, if you look at momentum conservation in this process of beta s gamma, so probably should have said this earlier. So when you look at beta S gamma, if you look at momentum conservation, then the p minus of the strange quark has to be equal to the p minus of the B quark, but that's just MB. Okay, so actually p minus is equal to MB by kinematics. So MBs in this result here you can think of as p minuses, and that's the things that this p bar that was in our Wilson coefficient is just getting set to MB because of some delta functions that are specifying kinematics. So that leaves the kind of 1 over epsilon terms. And so what we'd like is that those terms are associated to renormalization. Of the effective theory, right? I wrote that the effective theory was bare. But if I want to do that, then I have to ensure that all these epsilons that are appearing here are really ultraviolet divergences. If they're infrared divergences, then doing that doesn't make sense. And that's actually the remaining issue that we have to deal with. If I just wrote epsilon, that means I'm ignorant to what they are. And if I knew this one was epsilon IR because it came from the wave function normalization of the heavy quark, and that was the same on both sides. It was the same diagram as the wave function normalization diagram, the full and the effective theory, so I could match up that one. These ones just came out. But it turns out that so far, with what we've done, some of these epsilons here are IR. And so the IR divergences aren't matching up. And the reason is because we didn't put in those restrictions on our sum over labels. Okay, so we have these restrictions, k label not equal to 0, and k label not equal to minus PL. Those are the restrictions that I'm talking about. The place that those restrictions came from was K was the momentum of the gluon. KL not equal to 0 is saying that the gluon shouldn't be. This is the restriction that the gluon is collinear. Because KL equals 0 is the ultrasoft gluon. And this is the restriction that the fermion is collinear in the loop. That's why there was 2 of them. So these are called 0 bins. 0 because it's where the ultrasoft momentum lives, and that's kind of, from the point of view of collinear, that's 0. So imposing these restrictions is removing the 0 bin, if you like. And what these restrictions do is they avoid double counting. And the way I've said it, that's, I think, clearer. So far in our calculation, we haven't avoided double counting, and that's the problem. Okay, so we have to modify our rule, or we extend our rule to include the case where we have these restrictions. So in an extended version of Rule 2 that has restrictions. So really what we want to do is that. And we want to think about that as an integral. So here's how we can manipulate these to think about it as an integral. Let's sum over all KLs. But then we'll subtract the sort of, we'll subtract the limit of this f, where we take the f and we let the KL go to the place. So we integrate over everywhere, including the place we don't want to go, and we subtract and then we subtract it back. So what is this FL of k? This f of KL goes to 0. It's defined by taking the scaling limit of the collinear momenta towards the ultrasoft. So you take your collinear momenta, which are the minus and the perp here, and you scale them towards an ultrasoft momentum in whatever components, i.e. you start counting the kn's as order lambda squared, and you keep the leading order piece, or you keep the piece that's the same size as this term, and then that defines what this f is. It's once you take that limit and you expand, then that's what this f is. Okay. So what you're doing here by doing this procedure is you're basically setting things up so that this guy is integrated over in a way that we can combine back into an integral, but then we have to subtract kind of an overlap of when that integral would go into the ultrasoft region. But the overlap we're subtracting is also an integral. So we have a difference of integrals. And you should think of the second integral as kind of like the square, integrating over the square where the zero bin was. So if you think about our picture where the collinears were up here, ultrasofts are down here, and you thought about there being some box, you're taking the scaling limit when this guy goes down into that box. You add up all the boxes, that's this, and then you subtract out that box again. And that avoids having a double counting in that region. Okay, so then this guy here, you can do the same kind of trick as before. So continuing with the equation, KL is going to 0, we can think of it just as a function of KRs. And so effectively what we get in the end is an integral over all k of f of k, the full f, evaluated with a continuous momentum, minus some f that's expanded and avoids there being overlap in this box. So rather than having these discrete sum with a restriction, we have a difference of integrals, and this subtraction term avoids the overlap in that region. Okay? So all the discrete sums are good for is a means of figuring out what limits you need to take to generate these subtractions. And once you've done that, everything's a continuous integral. And this is called the zero bin subtraction. Okay, so if you like, one way of phrasing what's going on is that the collinear propagators are really distributions. They're distributions that know that there should be, that they should have a subtraction in order to not overlap the other region where we have another degree of freedom. So you could think about it that way, and this, having this sum is just a way of sort of encoding that. But in the end, it kind of looks like some kind of plus function where you have a subtraction.
So it seems like in the second term you would have to rewrite the expression because initially in your FFK you ignored KR
Yeah.
bonuses and KR perps.
I'll show you how it works in an example. I think it's clear. So let's go to our example. Yeah, it's not, so what you just said is not quite the way you should think about it. You should think about it that you've given the effective theory F. And now I'm saying that that F as given with its momentum as given still has an overlap with the ultrasoft region that I want to subtract. So I'm taking a limit of that F. I'm not adding anything back to it. So this guy, integral dk, so this is what we wrote before. And now if I take the ultrasoft limit of it, of the k, then I would write this. Okay, so when I take the scaling limit, if you think about k squared, it's k plus, k minus, minus k perp squared. When I take the scaling limit of all momentum being ultrasoft, the components of the k are still homogeneous, so there's nothing there to expand. Some expansion happened in this k plus p term. 1 over m bar dot k changes its power counting, but it's still m bar dot k, and there's nothing to expand there. So this is what the subtraction looks like. And in the numerator, the n bar dot k can be dropped relative to the m bar dot p, which is large and external. Okay, so this is taking the ultrasoft limit of this. Yeah, so in general, I would have to subtract off the ultrasoft limit of the quark as well. And when I do that, what I find is a term that's power suppressed, and so I drop it. But in general, I would have to do that as well. That's right. And so this is, it looks kind of like an ultrasoft diagram, except it's got this n bar dot k and instead of the v dot k that we had in the ultrasoft diagram. And if you do a power counting with the loop momentum scaling as ultrasoft, then this piece is of order the same size as this piece, and that's why you keep only that term.
Do you have to worry about a higher power?
No. So the prescription we have is that we drop the higher powers.
But if I wanted to do this calculation at higher power,
Oh, if you did the higher power.
Lower power, higher power 0 bin?
No. So if we did the higher power, then this would start out at higher power. And then when we took the limit of it, it would end up, just starting at that power or higher.
Right, but there was a
Yeah, you don't have to. You don't have to. No. No. Yeah.
Is there a reason?
Yeah. So it's kind of really what you care about subtracting here are the log divergences, and that's what this minimal subtraction is doing. By taking the piece that you're only keeping the piece that's scaling the same way, you're removing the log divergent pieces, and it's the log divergent pieces which are giving our 1 over epsilons. The pieces that you would get from the higher expansion, they would all be kind of like power law divergent terms from the point of view of the power counting, and we just don't have to worry about those. And another way of saying it is, it's not that I'm removing absolutely this whole integrand in that region, right? There could still be a constant, for example, that comes from that region. But if there's a constant that comes from that region, I don't care. What I care about removing is any spurious IR singularities. And for those, I can make a kind of minimal subtraction, which is just the first term. All right, so I want to finish this discussion. So if we do this, we get an answer, which is, I will try to write on the board for you. So now I'm going to distinguish all the epsilons, and then we'll see what this subtraction does. So if I was careful and I distinguished all the epsilons in our original calculation, it would actually look like this. And then the subtraction piece gives an extra contribution, and it's actually scaleless in the n bar.k here. There's a scaleless loop in this guy. So it actually vanishes if the epsilon IR and the epsilon UV are said to be equal. But what it does is it converts the epsilon IRs that are in the first expression into epsilon UVs, which is what we want. So once you add up these two things, the epsilon IRs are canceling. And the epsilon IRs that were coming in the original formula, those were coming about because of this bad behavior as n bar.k goes kind of into the ultrasoft, into the limit of sort of n bar.k going small. You can think about that roughly as where the ultrasoft is. This is kind of subtracting off that behavior. And the remainder then is coming from, you're only having divergences for sort of n bar.k goes to infinity, which is a sort of proper collinear ultraviolet divergence, not from n bar.k going to 0. So once you put the two together, the epsilon IRs cancel. And then we get exactly actually the same expression we had before, but where all those 1 over epsilons are 1 over epsilon UVs.
So the epsilon IRs come from the second term?
From both terms. So they both have epsilon IRs, but they cancel between them.
Okay.
Yeah. And the remainder is just epsilon UVs, so all the epsilons that I wrote in my earlier formula would be now epsilon UVs once I take into account the subtraction. So I could have just ignored the subtraction, and that's often what people do if they know that that the zero bins are kind of giving a scaleless integral. They say, well, let's ignore the subtraction. We'll just say that all the epsilons are UV, and the zero bin makes them UV. But if we really want to look and see that things are working properly, we should take the subtraction and calculate it and make sure that that's true. But we could have just taken the answer that I wrote down earlier and said those epsilons are ultraviolet, and let's throw them in a counter term and calculate an anomalous dimension. And that is indeed, so we'll proceed that way next time, but we now know that actually they are ultraviolet divergences. So next time we'll take the ultraviolet divergences and we'll define from them a counter term, and we'll see how we get an anomalous dimension and what kind of logs we sum by using that anomalous dimension. So the zero bin that's scaleless in this particular example is not always scaleless. So sometimes it could give a depends on the problem you're dealing with. So sometimes you can set things up so that it's scaleless and then you just basically can ignore it. But that's not always true, so you do have to think about whether it's really going to be true for what you're doing. If it is true, then you can effectively ignore it because it's sort of just making the physics come out right, making sure there's no overlap. But if your regulator is set up so that it's scaleless, you can kind of just get around it. But in general, that might not be true. If you had more scales in the problem, if you're doing some calculation that had some jets of finite size, then it won't be true, typically.